All right, so by now you're probably wondering what in the world any of this has to do with circuits, and this is where I'm going to talk about what it has to do with circuits. So basically, if we have a circuit, let's just draw something like a pulse with a resistor and a capacitor, because that's just my go-to example. This has some resistance R, some capacitance C. We could represent this by some time domain function V and of t. And let's say we were interested in finding the current flowing in this circuit, I of t. Well, right now you know that I of t is equal to the current through the capacitor, which is basically C times dVc dt. And so you'd have to go ahead and solve the differential equation to determine I of t here. And that's typically what you would do. So you have a time domain circuit. Uh-oh, I'm about to sneeze. Sorry. Okay, so you have a time domain circuit. You solve it using differential equations in the time domain, and you get a time domain solution, which is what we saw previously with these RC circuits. Of course, our time domain solution for something like Vc of t might have been, our final voltage multiplied by 1 minus e to the minus t over RC volts. And that is a time domain solution to a time domain circuit. We solve a differential equation and we obtain a time domain solution. Okay. Now, with the Laplace transform, we can basically have an alternative way to solve these circuits. If the differential equation is, say, too difficult, or if you just prefer Laplace, you can take the time domain circuit, transform it using Laplace transforms into an S domain circuit. We're going to see how to do that as we move forward in this module. I just needed to basically introduce the Laplace transform and the inverse Laplace transform before we could even talk about how to apply it to circuits. But we can take the Laplace transform of different elements and different functions and different voltage sources, etc., in a circuit. Then once we have an S domain circuit, we can solve that circuit using algebra in the S domain. So the nice thing is we don't have to use calculus. We can use algebra in the S domain because the transform makes it just a much simpler, more algebraic circuit to solve. And then once we get an S domain solution, we can take the inverse Laplace transform to move back to the time domain and end up with our original function. So here, there's a step-by-step procedure on how to use this Laplace transform to solve circuits. The first thing says you transform the circuit to the Laplace domain, also known as the S domain. In the S domain, you use KVL and KCL to yield a set of algebraic equations, so just solve using algebra. You solve these equations for whatever variable you're interested. Maybe it's V in, V out, maybe it's I out, maybe it's something else. And then with your S domain solution, you transform that back to the time domain using the inverse Laplace transform. So that is the procedure for how we apply this to circuits. Time domain circuit, Laplace transform it into the S domain, solve it using algebra, much easier than differential equations, and then take the inverse Laplace transform to get back to the time domain for our final solution, okay? I don't necessarily think this is super easy compared to differential equations. I think they're very different, and I think that differential equations can be difficult, but I also think that this can be quite difficult as well. So I don't think it's 100% easier method, but it is an alternative method, and so we need to talk about it. One last note here. This is kind of just showing the process. Again, this is a time domain circuit. We have this IS of t, this current pulse input, and we have resistor, inductor, and capacitor in the time domain with time domain expressions for the three currents. We transform this into the S domain. Here we have the impedance of the inductor in the S domain, the impedance of the capacitor in the S domain. S domain version of this input pulse, which we would have to model this as a difference of two unit step or two step functions. Okay, so we can go through that if someone has a question about it, but basically this I of S is now going to be a function of S. Okay, and IR, IL, and IC are all functions of S. And then once we get this S domain, let's say that what we were after in this particular circuit was something like IC of t. Let's say we get IC of S, then we need to take the Laplace inverse of IC of S to finally end up with IC of t, which is this equation here, or this function here, which we can see has some sinusoidal component, but it also has some exponentially decaying components. And there's also two different solutions here. There's a solution when the current is high, and there's a separate solution when the current is low. So we need to take that into account too. So these circuits can get pretty complicated. I'm going to try to keep our examples and the problems I assign to be less complicated than something like this, but just note that you can use Laplace to solve circuits that are even this complicated. Okay, so I'll end this video here, and in the next video, we're going to move into a little bit more about the Laplace transform now that we know how we can apply it to circuits.